So my name is Demaine. You should call me Eric. Welcome back to 6046. This is lecture 2. And today we're going to essentially fill in some of the more mathematical underpinnings of lecture 1. So lecture 1, we just sort of barely got our feet wet with some analysis of algorithms, insertion sort and merge sort. And we needed a couple of tools. We had this big idea of asymptotics and forgetting about constants, just looking at the lead term. And so today we're going to develop asymptotic notation to really, so that we know that mathematically. And we also ended up with a recurrence with merge sort, the running time of merge sort. So we need to see how to solve recurrences. And we'll do that, those two things today. Question?
Can you speak up just a little bit?
Yes, I will speak louder. Thanks. Good. Even though I have a microphone, I'm not amplified. Good. OK, so let's start with asymptotic notation. So we've seen some basic asymptotic notation. I'm sure you've seen it in other classes before. Things like big O notation. And today we're going to really define this rigorously so we know what's true and what isn't. What's valid, what isn't. Okay. So we're going to define, and unfortunately today is going to be really mathematical and really no algorithms today, which is sort of a anticlimax. But next lecture we'll talk about real algorithms and we'll apply all the things we learned today to real algorithms. So this is big O notation, capital O notation. So we have f of n equals big O of g of n. This means that there are some suitable constants, c and n naught, such that f is bounded by c times g of n for all sufficiently large n. Okay, so this is a pretty intuitive notion. We've seen it before. We're going to assume that f of n is non-negative here. And I just want f of n to be bounded above by g of n. So we've seen a bunch of examples, but something like 2 times n squared is big O of n cubed. Be fine. And roughly this means if you drop leading constants and lower order terms, then this is less than or equal to that. So big O corresponds roughly to less than or equal to. But this is the formalization. Another way to think of it formally as so a funny thing about this notation is it's asymmetric. Normally you think of equality being symmetric. If a equals b, then b equals a. But it's not true here. We don't have n cubed being big O of n squared. You don't even have big O of n cubed equaling n squared. So we'll see exactly what that means in a second. But before we get there, so this is a bit bizarre notation, and you should always think about what it really means. Another way to think about what it really means is that fn is in some set of functions that are like g. So you could define big O of g of n to be a set of functions, let's call it f of n, such that there exist constants. The same definition, nothing fancy here, c and n naught, such that we have the bound f of n is between 0 and c times g of n. Okay, it's a bit of a long definition, and that's why we use the notation, to avoid having to write this over and over. So you can think of, instead of n squared being equal to big O of n cubed, what we really mean is that 2n squared is in the set big O of n cubed. So this, when we write equal sign, we in some sense mean this in the set. But we're going to use equal sign. You could write this, and occasionally you see papers that write this, but this is the notation that that we're going to use. So that has the consequence the equal sign is asymmetric, just like this operator. Okay, we have some nifty ways that we actually use big O notation. It's using it as a macro. By the way, we have a lot to cover today, so I'm going to go relatively fast. If anything is unclear, just stop, ask questions, then I will slow down. Otherwise, I'll take this as all completely obvious, and I can keep going at full speed. Okay, so the convention, this is intuitive, I guess, if you do some macro programming or something. But it's a bit more mathematical. So we've defined big O notation and the equals big O of something. And so we've only defined big O when on the equal sign we have big O of some function. But it's useful to have some general expression on the right-hand side that involves big O. So for example, let's say we have f of n is n cubed plus order n squared. So this is attempting to get an error bound. This is saying fn is basically n cubed, but there's these lower order terms that are big O of n squared. And so this means that there's a function shorthand for a function, h of n, which is in big O of n squared, or equals big O of n squared, such that f of n equals n cubed plus h of n. So it's saying there's some lower order terms that are bounded above by some constant times n squared for sufficiently large n, and that's what's here. And then f of n equals, now this is a true equality, n cubed plus that error term. So this is very useful. Here, essentially, I'm expressing what the lead constant is, and then saying, well, there's other stuff, and it's all at most n squared. But saying that f of n, therefore, is also order n cubed, but that's a bit weaker of a statement. This is a bit more refined. We won't need to use this too often, but it's useful. Sometimes we'll see, like in last class, we even had a big O inside a summation. So you can use them all over the place. The point is they represent some function in that set. A bit less intuitive, and this is more subtle, is what it means to have big O on the left-hand side. It means the same thing, but there's some convention in what equality means. Okay, and this is why equal sign is asymmetric. Equals means, you should read equals like is. So is means that everything over here is something over here. So there's an implicit for all on the left-hand side, and there exists on the right-hand side. This is a true statement. Anything that is n squared plus big O of n is also big O of n squared, but not the other way around. So this is a bit asymmetric. This, if you think about it, this is pretty intuitive, but it's subtle, so you should be careful. So this says for any expansion of the macro on the left-hand side, which would be f of n, there's an expansion of the macro on the right-hand side such that we get equality. Okay, and what this allows you to do is if you have a chain of equal sign relations, a chain of is's, then the very first one is equal to or bounded by the very last one. So you can chain equal signs in the way you normally would, you just can't flip them around. Good. So that's big O notation. Any questions about that? Oof. Don't crush my fingers. So big O is great for expressing upper bounds, but we also want to talk about lower bounds. So For algorithms, we usually care about upper bounds on their running time. Running time is at most n squared. It's at most n log n, up to big O. But sometimes we need to express functions that are at least some quantity. For example, we'll show that sorting requires at least n log n time in some model. So we need some other notation for that. And the notation is big omega notation. And it's pretty symmetric. I'll just write out the set definition here. And we're going to write f of n is big omega of g of n to mean f of n is at least some constant times g of n. For sufficiently large n. So I'm basically just reversing the inequality relation between f and g. Nothing surprising, just to have it there. So a random example, and now we'll get a little bit more sophisticated. Root n is big omega of log n. And you should read this that up to constant factors, root n is at least log n for sufficiently large n. So omega sort of corresponds to greater than or equal to. So let me give you some analogies. We have big O, we have big omega. This is less than or equal to, this is greater than or equal to. And I'm going to fill in some more here in a moment. So, I mean, it's nice to have all the usual operators we have. So normally we have strict less than, strict greater than, and equal sign. And we want those sort of analogs in the asymptotic world where we ignore constant factors and ignore lower order terms. So we have, for example, theta of g of n. This is a capital theta, which means you write the horizontal bar in the middle as opposed to all the way through. I didn't invent Greek, so that's the way it is. Theta means that you're less than or equal to and you're greater than or equal to up to constant factors. So it's the intersection of these two sets, big O and big omega. So that's sort of like equal sign, but of course this is very different. So you have things like n squared is big theta of 2n squared, because you ignore constant factors. But all of these other relations, okay, n squared plus big O of n is going to be theta of n squared. But this does not hold with theta because square root of n is really bigger, asymptotically bigger than log n. And some of the other examples we saw, like n squared versus n cubed, those don't hold with theta. Okay, and we have some strict notation, which are the little o and little omega notations. There's no little theta, because there's no notion of strict equality versus unstrict equality. Little o is going to correspond roughly to less than, and little omega is going to correspond to greater than. This is notation you'll just have to get used to. And I'm not going to define it precisely here, because it's almost exactly the same. The difference is that instead of saying there exist constants c and n naught, you have to say for every constant c, there exists a constant n naught. So the relationship between f and g, this inequality, must hold for all c, instead of just for one. And so n naught can now depend on c. So you can assume that really n is sufficiently large. But this gives you a strict inequality. It says no matter what constant you put here in front of g, let's say we're doing little o, no matter what constant you put in front of g, f will be still less than c times g for sufficiently large n. So we have some random examples. And these are I mean, so we're again ignoring constants. N squared is always less than n cubed for sufficiently large n. And it's a bit subtle here. I mean, if you could work out, in order to prove something like this, it will become intuitive after you manipulate it a bit. You have to figure out what n0 is in terms of c. I think it's something like 2 over c. That should, if we have less than or equal to, that should be right. So as long as I choose, as long as n is at least this big, no matter how small of a c, you should think of c here as being epsilon now in the usual epsilon and deltas. No matter how small c gets, still I can bound n squared in terms of n cubed, upper bound. Okay, but you have, whenever you have theta, you do not have either of these relations. So for example, 1/2 n squared is theta of n squared, and it's not little o of n squared. And it's not little omega of n squared because it's exactly n squared. You get, in some sense, an order relation out of this, although there are some messy behaviors, as you'll see in your problem set. So any questions about asymptotic notation? That is the quick rundown. Now we're going to use it to solve some recurrences. Although we won't use it that much today, we'll use it a lot more on Wednesday. Okay. So we'll move on to the second topic of today, which is solving recurrences. You've probably solved some recurrences before in 6042, whatever discrete math class you've taken. We're going to do more and have some more techniques here that are particularly useful for analyzing recursive algorithms. And we'll see that mostly on Wednesday. There's 3 main methods that we're going to use here for solving recurrences. First one's the substitution method. And I mean, there's no general procedure for solving a recurrence. There's no good algorithm for solving recurrences, unfortunately. We have a bunch of techniques. Some of them work some of the time. And if you're lucky, yours will work for your recurrence. But it's sort of like solving an integral. You have to just know some of them. You have to know various methods for solving them. It's usually easy to check when if you have the right answer. Just like with integrals, you just differentiate, see, oh, I got the right answer. And that's essentially the idea of substitution method. So substitution method will always work. But unfortunately, step 1 is guess the answer. And you have to guess it correctly. That makes it a bit difficult. You don't have to guess it completely. You can usually get away with not knowing the constant factors, which is a good thing because we don't really care about the constant factors. So you guess the form, you say, oh, it's going to be roughly n squared. And so it's some constant times n squared, presumably. So you guess that. We're going to figure out the constants. You try to verify whether the recurrence is satisfies this bound by induction. And that's the key. Substitution uses induction. And from that, you usually get the constants for free. Figure out what the constants have to be in order to make this work. So that's the general idea. See a few examples of this. Actually, the same example several times. Okay, unfortunately, this is what you might call a, I don't know. This is an algorithm, but it uses an oracle, which is knowing the right answer. But sometimes it's not too hard to guess the answer. Depends. So if you look at this recurrence, t of n is 4 times t of n over 2 plus n. We should implicitly, we always have some base case of t of some constant, usually 1, is a constant. So we don't really care about the base case. For algorithms, that's always the case. And we want to solve this thing. Does anyone have a guess what the solution is? Ideally, someone who doesn't already know how to solve this recurrence. OK, how many people know how to solve this recurrence? A few. OK. And of the rest, any guesses? So if you look at what's going on here, here you have t of n over 2. Let's ignore this term, more or less. We have n over 2 here. If we double n and get t of n, then we multiply the value by 4. And then there's this additive n, but that doesn't matter so much. So what function do you know that when you double the argument, the output goes up by a factor of 4? Sorry? N squared, yeah. So you should think n squared, and you'd be right. Okay, but we won't prove n squared yet. Let's prove something simpler, because it turns out proving that it's at most n squared is a bit of a pain. We'll see that in just a few minutes. But let's guess that t of n is n cubed first, because that will be easier to prove by induction. So you sort of see how it's done in the easy case, and then we'll actually get the right answer, n squared, later. So I need to prove, what I'm going to do is guess that t of n is some constant times n cubed at most. So I'll be a little more precise. I can't use the big O notation in the substitution method. So I have to expand it out to use constants. I'll show you why in a little bit. Let me just tell you at a high level what's important in not using big O notation. So big O notation is great if you have a finite chain of big O relations. You know, n squared is big O of n cubed, is big O of n to the fourth, is big O of n to the fourth, is big O of n to the fourth. That's all true, and so you get that n squared is big O of n to the fourth. But if you have an infinite chain of those relations, then the first thing is not big O of the last thing. So you have to be very careful. For example, right, this is a total aside in the lecture notes. Suppose you want to prove that n equals order 1. This is a great relation. If it were true, every algorithm would have constant running time. So this is not true. That's right, not in Wayne's World notation. So you could prove this by induction. You could prove this by induction by saying, well, base case is 1 equals order 1. OK, that's true. OK, and then the induction step is, well, if I know that n minus 1, so let's suppose that n minus 1 is order 1. Well, that implies that n, which is n minus 1 plus 1, well, if this is order 1, and this 1 is order 1, so the whole thing is order 1. And that's true. If you knew that n minus 1 was order 1 and 1 is order 1, then their sum is also order 1. But this is a false proof. You can't induct over big O's. What's going on here is that the constants that are implicit in here are changing. Here you have some big O of 1. Here you have some big O of 1. You're probably doubling the constant in there every time you do this relation. If you have a finite number of doublings of constants, no big deal. It's just a constant, 2 to the power number of doublings. But here you're doing n doublings, and that's no good. So the constant is now depending on n. So we're avoiding this kind of problem by writing out the constant. We have to make sure that constant doesn't change. So good. OK, so now I've written out the constant. I should be safe. What I need to prove, this is, I'm assuming it for all k less than n, and now I have to prove it for k equal to n. So I'm going to take t of n and just expand it. OK, I'm going to do the obvious thing. I have this recurrence, how to expand t of n. Then it involves t of n over 2, and I know some fact about t of n over 2 because n over 2 is less than n. So let's expand. T of n is 4 times t of n over 2 plus n. And now I have an upper bound on this thing from the induction hypothesis. So this is at most 4 times c times the argument cubed plus n. I have a feeling by the end of the lecture, these blackboards will be totally stuck. Oh, boy. No, it's not going up. OK. It's OK. I only need half a board. I'd like to say it's from my superhuman strength, but I believe it's from the quality of the blackboards or their hinges. OK, so continuing on here, let's expand this a little bit. So we have 4. OK, so we have n cubed over 2 cubed. 2 cubed is 8, so 4 over 8 is a half. So we have a half times c times n cubed plus n. And what I'd like this to be is, so at the bottom where I'd like to go, is that this is at most c times n cubed. That's what I'd like to prove to reestablish the induction hypothesis for n. So what I'll do in order to see when that's the case is just write this as what I want. So this is sort of the desired value, c times n cubed, minus whatever I don't want. So this is called the residual. So now I have to actually figure this out. See, we have cn cubed, but only half cn cubed here, so I need to subtract off half cn cubed to get that lead term correct. And then I have plus n, and there's a minus here, so it's minus n. Okay, and that's the residual. In order for this to be at most this, I need that the residual is non-negative. So this is if the residual part is greater than or equal to 0, which is pretty easy to do because here I have control over c. I get to pick c to be whatever I want. And as long as c is at least, I don't know, 2, then this is a 1, at least. And I have n cubed should be greater than or equal to n. And that's always the case. So this is, for example, oh boy. This is true if c is at least 1. And I don't think it matters what n is. But let's say n is at least 1, just for kicks. OK, so we get what we've done is prove that t of n is at most some constant times n cubed, and the constant is like 1. So that's an upper bound. It's not a tight upper bound. We actually believe that it's n squared, and it is. But you can, so you have to be a little careful. This does not mean the answer is n cubed. It just means that it's at most n cubed. It's big O of n cubed. And this is a proof by induction. Now, technically, I should have put a base case in this induction. So there's a little bit missing. The base case is pretty easy because t of 1 is some constant. But it will sort of influence things. So if the base case, t of 1 is some constant. And what we need is that it's at most c times 1 cubed, which is c. And that will be true as long as you choose c to be sufficiently large. So this is true if c is chosen sufficiently large. Now, we don't care about constants, but the point is just to be a little bit careful. It's not true that t of n is at most 1 times n squared, even though here all we need is that c is at least 1. For the base case to work, c actually might have to be 100 or whatever t of 1 is. Okay, so be a little bit careful there. It doesn't really affect the answer. Usually it won't, but because we have very simple base cases here. OK, so let's try to prove the tight bound of order n squared. I'm not going to prove an omega bound, but you could prove an omega n squared bound as well using substitution method. I'll just be satisfied for now proving an upper bound of n squared. So let's try to prove that t of n, this is the same recurrence. I want to prove that it's order n squared. So I'm going to do the same thing, and I'll write a bit faster because this is basically copying. Except now, instead of 3, I have 2. So then I have t of n is 4 times t of n over 2 plus n. I expand this t of n over 2. This is at most 4 times c times n over 2 squared plus n. And now, instead of having 2 cubed, I have 2 squared, which is only 4. 4's cancel. I get c times n squared plus n. And if you prefer to write it as desired minus residual, then I have c n squared minus negative n. And what I need is that I want this to be non-negative. And it's damn hard for minus n to be non-negative. If n is 0, we're happy. But unfortunately, this is an induction on n. It's got to hold for all n greater than or equal to 1. So this is not less than or equal to Cn squared. Notice the temptation is to write that this equals big O of n squared, which is true for this one step. Okay, C times n squared minus n. Well, I mean, these are both order n. Or this is order n, this is order n squared. So certainly this thing is order n squared. That's true, but it's not completing the induction. To complete the induction, you have to prove the induction hypothesis for n with this constant c. Here you're getting a constant c of like c plus 1, which is not good. So this is true, but useless. Okay, it does not finish the induction. So you can sort of ignore that. This proof doesn't work, which is kind of annoying because we feel in our heart of hearts that T of n is n squared. It turns out, to fix this, you need to express T of n as a slightly different form. This is, again, divine inspiration. And if you have a good connection to some divinity, you're all set. But it's a little bit harder for the rest of us mere mortals. It turns out, and maybe you could guess this, so the idea is we want to strengthen the induction hypothesis. So we assumed this relatively weak thing, T of k, is at most some constant times k squared. We didn't know what the constant is. That's fine. But we assumed that there were no lower order terms. I want to look at lower order terms. Okay, maybe they play a role. And if you look at this progression, you say, oh, well, I'm getting something like n squared, and the constants are pretty damn tight. I mean, the 4s are canceling. The c just is preserved. How am I going to get rid of this lower order term plus n? Well, maybe I could subtract off a linear term in here, and if I'm lucky, it'll cancel with this one. Okay, that's all the intuition we have at this point. Turns out it works. So we look at T of n. This is 4 times T of n over 2 plus n, as usual. Now we expand a slightly messier form. We have C1 times n over 2 squared minus C2 times n over 2 plus n. Okay, this part is the same. The 4's cancel again. So we get C1 times n squared, which is good. I mean, that's sort of the form we want. Then we have something times n. So let's figure it out. We have a plus 1 times n. So let's write it 1 times n minus C2 over 2 times n. Oh, no, got that wrong. So there's a 4 times a 2. So in fact, the 2 is upstairs. Double check. Right. OK, so now we can write this as desired minus residual. And we have to be a little careful here because now we have a stronger induction hypothesis to prove. We don't just need it's at most C1 times n squared, which would be fine here because we can choose C2 to be large. But what we really need is the C1 n squared minus C2 times n. And then minus some other stuff. So this is, again, desired minus residual. And minus residual, let's see, we have a minus 1, and we have a minus C2. It doesn't look so happy. C2 minus 1 plus C2. Thank you. Whew. That again looked awfully negative. Yeah, it's plus C2. I'm getting my sign errors. There's a minus here, and there's one minus here. So there we go. So again, I want my residual to be greater than or equal to 0. And if I have that, I'll be all set in making this inductive argument. So office hours start this week, in case you're eager to go. They're all held in some room in building 24, which is roughly the midpoint between here and Stata, I think, for no particular reason. Good. And you can look at the webpage for details on the office hours. So continuing along, we want, when is C2 minus 1 going to be greater than or equal to 0? Well, that's true if C2 is at least 1, which is no big deal. Again, we get to choose the constants however we want. It only has to hold for some choice of constants. So we can set C2 greater than or equal to 1. So then we're happy. That means, so this whole thing is less than or equal to C1n squared minus C2n if C2 is greater or equal to 1. So it's kind of funny here. We have this. We've proved now. This finishes the induction, at least the induction step, for any value of C1, and provided C2 is at least 1. It's a little. We have to be a little more careful if C1 does actually have to be sufficiently large. Any particular reason why? C1 better not be negative. Indeed, C1 has to be positive for this to work. But it even has to be larger than positive, depending. Sorry, I've been going so fast I haven't asked you questions. Now you're caught off guard. Yeah. Because of the base case, exactly. So the base case will have T of 1 is, C1 times 1 squared minus C2. And by this, or we want to prove that it's at most this. And T of 1 is some constant, we've assumed. So we need to choose C1 to be sufficiently larger than C2, in fact. So C2 has to be at least 1. C1 may have to be at least 100 more than 1 if this is 100. So this will be true if C1 is sufficiently large. And sufficiently large now means with respect to C2. So we have to be a little bit careful, but in this case, it doesn't matter. Any questions about the substitution method? That was the same example 3 times. In the end, it turned out we got the right answer. But we sort of had to know the answer in order to find it, which is a bit of a pain. It'd certainly be nicer to just figure out the answer by some procedure, and that will be the next 2 techniques we talk about. Sorry? How would you prove a lower bound? I haven't tried it for this recurrence, but you should be able to do exactly the same form. Argue that T of n is greater than or equal to C1 times T n squared minus C2 times n. I didn't check whether that particular form will work, but I think it does. So try it. These other methods will give you, in some sense, upper and lower bounds, if you're a little bit careful. But to really check things, you pretty much have to do the substitution method, and you'll get some practice with that. Usually we only care about upper bounds. So proving upper bounds like this is what we'll focus on. But occasionally we need lower bounds. It's always nice to know that you have the right answer by proving a matching lower bound. So the next method we'll talk about is the recursion tree method. And it's a particular way of adding up a recurrence. And it's my favorite way. It's particularly, it usually just works. That's the great thing about it. It provides you intuition for free. It tells you what the answer is, pretty much. It's slightly non-rigorous. This is a bit of a pain. So you have to be really careful when you apply it. Otherwise, you might get the wrong answer. Because it involves ... dots, our favorite 3 characters. But ... dots are always a little bit non-rigorous, so be careful. Technically, what you should do is find out what the answer is with the recursion tree method, then prove that it's actually right with the substitution method. Usually that's not necessary, but you should at least have in your mind that that is required rigorously. And probably the first few recurrences you solve, you should do it that way. When you really understand the recursion tree method, you can be a little bit more sloppy if you're really sure you have the right answer. So let's do an example. We saw recursion trees very briefly last time with merge sort as the intuition of why it was n log n. And this, if you took an example like the one we just did with the recursion tree method, it's dead simple. So just to make our life harder, let's do a more complicated recursion. So here, we imagine we have some algorithm, starts with a problem of size n. It recursively solves a problem of size n over 4. It then recursively solves a problem of size n over 2. And it does n squared work on the side without non-recursive work. So what is that? That's a bit less obvious, I would say. So what we're going to do is draw a picture of how we're just going to expand out that recursion in tree form. And then just add everything up. So we want to, the general picture, and the general principle in recursion tree method is we just draw this as a picture. We say, well, T of n equals the sum of n squared T of n over 4 and T of n over 2. So, I mean, this is a weird way of writing a sum, but why not write it that way? Okay, this is going to be a tree, and it's going to be a tree by recursively expanding each of these two leaves. So I start by expanding T of n to this, then I keep expanding everything. So let's go one more step. We have this n squared T of n over 4, T of n over 2. If we expand one more time, this is going to be n squared plus two things. The first thing is going to be n over 4 squared. Second thing is going to be n over 2 squared plus their recursive branches. So we have T of n over 16 and T of n over 8. Here my arithmetic shows thin. This better be the same, T of n over 8, and this should be T of n over 4, I believe. Okay, you just keep going forever. I mean, until you get down to the base case where T is a constant. Okay, so I'm going to now skip some steps and say dot, dot, dot. This is where you have to be careful. So we have n squared, n over 4 squared, n over 2 squared. Now this is easy because I've already done them all. N over 16 squared, n over 8 squared, n over 8 squared again, n over 4 squared, and etc. Dot, dot, dot. Various levels of recursion here. At the bottom, we're going to get a bunch of constants. These are the leaves. Okay. I'd like to know how many leaves there are. So that's one challenge, is how many leaves in this tree could there be? This is a bit subtle, unlike merge sort or unlike the previous recurrence we solved. The number of leaves here is a bit funny because we're recursing at different speeds. This tree is going to be much smaller than this tree. It's going to have smaller depth because it's already gone down to n over 16. Here it's only gone down to n over 4. But how many leaves are there in this recursion tree? All I need is an upper bound. Some reasonable upper bound. I can tell you it's at most n to the 10th, but that's a bit unreasonable. Should be less than n. Good. Why is it less than n? Exactly. So I start with a problem of size n, and I recurse into a problem of size n over 4 and a problem of size n over 2. When I get down to 1, I stop. So n over 4 plus n over 2 is 3/4 n, which is strictly less than n. So definitely, the total number of leaves has to be at most n. Because I start out with n sort of stuff, and I get rid of 1/4 of it and then recurse. And so it's definitely going to be less than n stuff at the bottom. So strictly less than n leaves. Okay, at this point, I've done nothing interesting. And then the second cool idea in recursion trees is you don't just expand this tree and see what it looks like and then say, well, God, how the hell am I going to sum that? You sum it level by level. That's the only other idea. It usually works really, really well. Okay, here it's a bit complicated. I have to think a bit to figure out n squared is n squared. That's the first level. Okay, easy. Second level, I have to think a lot harder because there are three kinds of mathematicians, those who can add and those who can't. And I'm the latter kind. So I need your help. Can you add these things together? It's n squared over something. Please? Oh, 5 over 16. Good. Thanks. 5 over 16 n squared. OK, now I really need your help. I think that one I could have done, but this is a little bit harder. I'll go look at my notes while you compute that. Where did I? Any answers? 7 over 256? 73 over 256. Anyone else confirm that? That seems a bit high to me. 73 doesn't sound right. I could cheat. 64? Closer. It's actually important that we get this right. The 256 is correct. I can tell 256, so everyone should know 16 squared is 256. We're computer scientists. 25, good. We have 2 people saying 25, therefore it's correct by democracy. 25 is also what my notes said, and I computed it at home. 25 is the right answer. Now, anyone notice something magical about this progression? It squares each time, good. And if we were going to add these up, you might call it a geometric series. Very good. So it turns out this is geometric. And we know how to sum geometric series, at least you should. So let's see. Oh, almost. So we start at n squared. We know that at the bottom well, this is not quite a level. We get something like n. But we're decreasing geometrically. Okay, so the total is sort of the total. I mean, we know the solution of the recurrence is the sum of all the numbers in this tree. So if we add it up level by level and then add up all the levels, that's going to give us the answer. So this is the total computed level by level. It's just a cute way to compute it. Usually gives you nice answers like geometric answers. So we have 1 times n squared plus 5/16 times n squared. And if we believe in fate and we see this 3-number recurrence, we know that we have the right answer. In general, it's going to be 5 to the power k over 16 to the power k, at least we hope, and so on. And it keeps going. It doesn't go on infinitely, but let's just assume it goes on infinitely. That will be an upper bound. It goes on forever. This is all times n squared. Okay, now, if you're going to know one thing about geometric series, you should know that 1 plus a half plus a quarter, if you sum all the powers of 2, you get 2. Good. Okay, we're computer scientists. We've got to know at least the binary case. This is like writing 0.111111 in binary. Actually, 1.1111. And 1111 forever is the same as 1. So this is 2. This is even smaller. We have 5/16. That's less than a half, and then we're squaring each time. So this is even less than 2. Okay, if you want, there's a nifty formula for solving the general geometric series, but all we need is that it's a constant. So this is order n squared. Okay, it's also omega n squared. It's pretty obvious that it's omega n squared because the top thing is n squared. So there's our lower bound of n squared. And we have it within a factor of 2, which is pretty good. You actually get a better factor here. So that's the recursion tree method. It's a little shaky here because we have these ... dots, and we just believe that it's geometric. Turns out most of the time it's geometric, no problem. Here I would definitely check it with the substitution method because this is not obvious to me that it's going to be geometric. In the cases we'll look at in a moment, it will be much clearer. So clear that we can state a theorem that everything is working fine. Okay, and still time. Good. So that was recursion trees. There's one more method we're going to talk about, and you could essentially think of it as an application of the recursion tree method, but it's made more precise. And it's an actual theorem, whereas recursion trees, you better, if the ... dots aren't obvious, you better check them. The sad part about the master method is it's pretty restrictive. It only applies to a particular family of recurrences. So it should be T of n equals a, some constant a times T of n over b plus some function of n. We're going to call it f. Yes, I'll call it f. So in particular, it will not cover the recurrence I just solved because I was recursing on 2 different problems of different sizes. Here, every problem you recurse on should be of the same size. There's a subproblems. I mean, think of this as a recursive algorithm. You have a subproblems. Each of them is of size n over b. So the total cost will be this. Then you're doing f of n non-recursive work. Few constraints. A should be at least 1. It should have at least 1 recursion. B should be strictly greater than 1. You better make the problem smaller or else it's going to be infinity. And f should have some nice property. F of n should be asymptotically positive. So how many people know what asymptotically positive means? No one. Okay, you haven't read the textbook. That's okay. I haven't read it either, although don't tell Charles. And he'd notice. And what might you think asymptotically positive means? Okay, that we can do a little bit better. Sorry? Yes, it means for large enough n, f of n is positive. Okay, this means f of n is greater than 0 for n, at least some n naught. So for some constant n naught. So eventually it should be positive. I mean, we don't care about whether it's -1 for n equals 1. Not a big deal. It won't affect the answer because we only care about the asymptotics with n. Good. So the master method, you give it a recurrence of this form, it tells you the answer. That's the great thing about the master method. The annoying thing about the master method is it has 3 cases. It's a bit long. It takes a little bit longer to memorize than all the others because the others are just ideas. Here we need to actually remember a few things. So let me state the theorem. Well, not quite yet. There is one very simple idea, which is we're going to compare this non-recursive work f of n with a very particular function n to the log base b of a. Okay, why n to the log base b of a? You'll see later. Turns out it is the number of leaves in the recursion tree, but that's the foreshadowing. So it's either less, equal, or bigger. And here we care about asymptotics, and so we have to be a little bit more precise about less, equal, or bigger. You might think, well, it means little o, big theta, or little omega. And it would be nice if the theorem held for all of those cases, but it leaves some gaps. Okay, so let's start with case 1. Case 1 is when f is smaller, and not just that it's little o, but it's actually quite a bit smaller. It's got to be polynomially smaller than n to the log base b of a. So for some positive epsilon, the running time should be this n to this constant log base b of a minus that epsilon. So it's really polynomially smaller than n to the log base b of a. We can't handle the little o case. That's a little bit too strong. This is saying it's really quite a bit smaller. OK, but the answer then is really simple. T of n is theta n to the log base b of a. Great. That's case 1. Case 2 is when f of n is pretty much equal to n to the log base b of a. And by pretty much equal, I mean up to polylog factors. So this is log base 2 of n to the power k. Should know this notation. So for example, k could be 0. And then they're equal up to constant factors. This is for some k greater than or equal to 0. Less than will not work, so it's really important that k is non-negative. Should probably be an integer. No, it doesn't actually matter whether it's an integer. But there it is. Could be n to the log base b of a times log n, or just times nothing, whatever. OK, again, solution is easy here. T of n is n to the log base b of a times, presumably has to be at least times log k. Turns out it's log to the k plus 1 of n. That's case 2. We have one more case, which is slightly more complicated. We need to assume slightly more for case 3. But case 3 is roughly when f of n grows bigger than n to the log base b of a. So it should be capital omega. Here's one place where we get to use omega. Log base b of a plus epsilon for some positive epsilon. So it should grow not just bigger, but polynomially bigger. Here it was growing just a log factor bigger, polylog. Here it's a polynomial factor. Here, in this case, we need another assumption about f, because we worry a little bit about how quickly f grows. We want to make sure that as you go down the recursion, f gets smaller. It'd be kind of nice if f gets smaller as you go down. Otherwise, you're again trying to sum to infinity or whatever. Yeah, I see. This is some epsilon prime for some epsilon prime greater than 0. So what I'd like is that if I just sort of take the recurrence, this t of n, and just throw in f's instead, I get, f of n should be somehow related to a times f of n over b. What I'd like is that f of n, which is at the top of the recursion tree, should be bigger than the thing at the next level down. The sum of all the values at the next level down should be bigger by some constant factor. So here I have that the next level down is at most some 1 minus epsilon, something strictly less than 1, some constant strictly less than 1 times the thing at the top level. Okay, I need that to make sure that things are getting smaller as I go down. Then t of n is theta f of n. And that's the theorem. This is the master theorem, or whatever you want to call it. It's not named after some guy named Master. It's the master of all methods, because it's very easy to apply. So let's apply it a few times. And it's a bit much to take in all at once. And then I'll give you a sketch of the proof to see it's really not that surprising that this is true if you look at the recursion tree. But first, let's just try using it. So for example, we could take t of n is 4 times t of n over 2 plus n. Okay, this is a, this is b, this is f of n. Okay, so the first thing we should compute is n to the log base b of a. This, I think, even I can do. Log base 2 of 4. Yeah, log base 2 I can do. This is n squared. Okay, so is f of n smaller or bigger than n squared? Well, f of n is n. N squared is clearly bigger by a polynomial factor. So we're in case 1. So what's the answer? N squared, yeah. It's theta n to the log base b of a, which is here just n squared. Let's do some slight variation. So I'm going to keep a and b the same and just change f. So let's say t of n is 4 times t of n over 2 plus n squared. Okay, this is like drill, spelling. So n squared is asymptotically the same as n squared, even up to constants. So what's the answer? This is case 2. Slightly harder. What's k in this example? 0. So the answer is, survey says, n squared log n. Good. And a couple more. T of n is 4 times t of n over 2 plus n cubed. What's the answer? n cubed. This is case 3. Okay, I know this is pretty boring. At this point, we're just applying this stupid theorem. How about n squared divided by log n? What's the answer? Good. In this case, no one should answer. It's a bit tricky. I forget exactly the answer. I think it's like n squared log n over log n, no? Oh, no, n squared log n. That's right. Yeah. But you should know that. This doesn't follow from the master method. This is something you'd have to solve. Probably with a recursion tree would be a good way to do this one. And you need to know some properties of logs to know how that goes. But here, the master method does not apply. So you have to use a different method. Good. Okay, the last thing I want to do is tell you why the master method is true. And that makes it much more intuitive, especially using recursion trees, why everything works. I shouldn't bring that down, unless I can get this one up. Hey, that one slides well. That one doesn't. So we're going to prove, this is a sketch of a proof, not the full thing. You should read the proof in the textbook. It's not that much harder than what I'll show, but it's good for you to know the formal details. I don't have time here to do all of the details, just to tell you the salient parts. So this is the proof sketch, or the intuition behind the master method. So what we're going to do is just take the recursion tree for this recurrence and add up each level, and then add up all the levels, see what we get. So we start with f of n at the top after we've expanded one level. Then we get a different problems, each of size n over b. And after we expand them, it'll be f of n over b for each one, because they're all the same size. Then we expand all of those and so on. We get another a subproblems from there. We're going to get like f of n over b squared. So that's sort of decreasing geometrically, the size, and so on and so on and so on, until at the bottom we get constant size problems. This is a bit special because this is the base case, but we have some other constant at the bottom. We'd like to know how many leaves there are, but that's a little bit tricky at the moment. So let's first compute the height of this tree. Let me draw it over here. So what is the height of this tree? I start with a problem of size n. I want to get down to a problem of size 1. How long does that take? How many levels? This is probably too easy for some and not at your fingertips for others. Log base b of n, good. The height of this tree is log base b of n, because it's just how many times do I divide by b until I get down to 1. So that's great. Now I should be able to compute the number of leaves, because I have branching factor a, I have height h. So the number of leaves is a to the h, a to the log base b of n. So let me expand that a little bit. A to the log base b of n. Properties of logs, we can take the n downstairs and put the a upstairs, and we get n to the log base b of a. Our good friend n to the log base b of a. So that's why n to the log base b of a is so important in the master method. What we're doing is comparing f, which is the top level, to n to the log base b of a, which up to thetas is the bottom level. Right now, the leaves are all at the same level, because we're decreasing at the same rate in every branch. So if I add up the cost at the bottom level, it is theta n to the log base b of a. I add up the things at the top level, it's f of n, not terribly exciting. That the next level, this is a little bit more interesting, is a times f of n over b, which should look familiar if you had the master method already memorized. It's that. Okay, so we know that a times f of n over b has decreased by some constant factor, 1 minus epsilon prime. So we've gone down. This is a constant factor smaller than this. And then you sum up the next level, it's going to be like a squared times f of n over b squared. Yeah, I see that I actually wrote this wrong. Parentheses, sorry about that. It's not n over b squared, it's n over b squared. So this sequence is, in case 3 at least, it's decreasing geometrically. If it's decreasing geometrically up to constant factors, it's dominated by the biggest term, which is f of n. Therefore, in case 3, we get theta f of n. Let's look at the other cases, and let me adapt those cases to how much time we have left. Wow, lots of time. 5 minutes, tons of time. OK, what to do? OK, let's start. Let me write that down. So case 3, the costs decrease. Now, this is a place I would argue where the dot, dot, dot is pretty obvious. Right here, this is damn simple. It's a to the k times f of n over b to the k. And in case 3, we assume that the costs decrease geometrically. As we go down the tree. OK, that was sort of backwards to start with case 3. Let's do case 1, which is sort of the other intuitively easy case. So in case 1, we know that f of n is polynomially smaller than this thing. And we're sort of changing by this very simple procedure in the middle. I'm going to wave my hands, and this is where you need a more formal argument. I claim that this will increase geometrically. It has to increase geometrically because this f of n is polynomially smaller than this one. You're going to get various polynomials in the middle, which interpolate geometrically from the small one to the big one. Therefore, the big one dominates because it's, again, geometric series. As I said, this is intuition, not a formal argument. This one was pretty formal because we assumed it. But here you need a bit more argument that they may not increase geometrically, but they could increase faster. And that's also fine. So in case 3, you're dominated. You're always dominated by the big term, by the biggest term in a geometric series. Here it happens to be f of n. And here you're dominated by n to the log base b of a, with the bottom term, theta. OK, case 2, a little bit, here it's pretty easy, but you need to know some properties of logs. In case 2, we assume that all of these are basically the same. We assume that the top is equal to the bottom. And this is changing in this very procedural way. Therefore, all of the ones in the middle have to be pretty much the same. Okay, not quite, because here we don't have the log factor. So here we have a log to the k. We have n to the log base b of a times log to the kn. Here we don't have the log to the k. So the logs do disappear here. Turns out the way they disappear is pretty slowly. Most of these, if you look at the top half of these terms, hope it's half, they will all have log to the k. And then the bottom half, they'll start to disappear. I'm giving you some oracle information. If you take logs and you don't change the argument by too much, the logs remain. Maybe halfway is too far. But the claim is that each level is roughly the same, especially the uppermost levels are all asymptotically equal. Roughly the same. And therefore, the cost is one level, which here like f of n, times, old school, times the number of levels, h. And h is log base b of n. B is a constant, so we don't care. This is theta log n. And therefore, we get that t of n is n to the log base b of a times log to the kn times another log n. So we get f of n times log n. That is the very quick sketch. Sorry, I'm being pretty fuzzy on cases 1 and 2. Read the proof, because it will really, you'll have to at some point manipulate logs in that way. And that's all. Any questions? We're all eager to go. Okay, thanks. See you Wednesday.